wasn't all that bad. We will have that graded as soon as possible, hopefully early this part of the week. Otherwise, we're back into regular week-to-week stuff where you've got labs and hacks due every week now until we get to the midterm in a few weeks. The midterm is going to be a little bit more substantial. The first exam was intentionally simple, just to keep it light and to make sure that you've mastered the basics that have been covered in the first few weeks here. Don't mistake the first 4 weeks for how the rest of the course will go, because we're going to get into more complex topics as we build on those basic topics. And one of those complex topics we're going to start talking about today. So remember 2 weeks ago, I guess it would be now, well over a week ago, I showed you how functions actually work. That when you call a function, that we've got this thing called the program stack. And when a function is called, a new stack frame is created on top of that stack. When that function calls another function, a new stack frame is created and it builds on it, right? Until you get to the end of a function and it returns, well, then that stack frame is popped off the top of the stack, right? And for that reason, we witnessed that this swap program doesn't work, right? An attempt to swap A and B over here is not going to work. That I've got A and B are 10 and 20 in the main, right? When I print those out, of course, it will be 10 and 20. But when I go and jump into the swap here and I receive the values 10 and 20, clearly those are values in a different stack frame. A and B are not the same variables as before, right? So when I go to swap them, of course it will work, but it will only work on the A and B that live inside this swap function, right? Inside this stack frame here. So when I print them out, of course it'll look like they're swapped, but those are not the same A and B in the main, right? When I come back to main, now that entire stack frame has been popped off, it's gone. Those two variables are now dead, right? They're out of scope. There's no way to retrieve them, right? And in fact, attempts to retrieve them will result in a stack smashing event that I tried to invoke. Maybe I can try offline to find an example where I can force a stack smashing event. But otherwise, when I print these out, of course, A and B are unchanged. So though they were changed in the function, right, they were swapped successfully there, the originals are not there. So my goal today is I really want to do that. I really want to swap these so that A and B here are swapped, right? It's kind of a trivial task. Why would you actually want to do this? But it gives us an opportunity to start talking about pointers in C. So in C, and in fact in any programming, in every piece of data, right, in a computer is stored in memory. Right? And I don't have, well, maybe I have an example here. Let's see if I can pull one up. That's just from my book, probably. What does memory look like? Nope. Nope. Oh, darn it. Oh, well. Let's do a Google image search for computer memory address. What does computer memory actually look like? These aren't very good. These aren't very good. Memory address contents. This is getting probably the closest here, where we've got memory here that all that's stored in there are a bunch of zeros and ones. But how do you know where to access things? Memory consists of two parts: an address and then the contents stored at that address. Okay. You know what? I'm going to take the time and pull up the book on that. I should have done this before, but sorry. Come on. So I don't know how many people have been doing the actual reading. No? Yes? All right. There we go. I knew it wouldn't take that long to find it. All right, so pay attention to the first one over here, right? We've got an address, and an address is just a number, right? Just like physical addresses, you know, you live at 1234 ABC Street, right? But what's actually in the house, the people that live in the house, those are the contents of the house, right? So in memory is exactly like that. We've got an address, but then we've also got the content, whatever's stored at that address. Okay. So every piece of data in a computer is stored in memory, right? Memory consists of an address, its location, and its contents, the actual data stored. Right? In C, you can refer to an address using a pointer or a reference variable. We're just going to call them pointers though, right? A pointer stores a memory location, right? An address rather than a value. Okay? To create a pointer, use the star actually spelled it out. The star syntax, right? So what syntax, there we go. So what I'm going to do is I'm going to go back over here to my IDE, and we're going to go ahead and start typing some code here. Now this is a regular old variable. Int x is equal to 42, right? 42 is the contents. So if I were to look at this diagram here again, the contents somewhere over here would be the value stored as 42. But what's its actual address? Right? To do that, I need a pointer. So let me go ahead and create an integer pointer called ptr to x. Right? There's the syntax for creating a pointer. The only difference is that you've got this star here. Now, white space generally doesn't matter. You could declare it like this. You could declare it like this. But I'm going to go ahead and go with this style right here. All right? Int space star and then the name of the pointer, the name of the variable. Right? So at this point in the program, what does this pointer point to? This is why we call them pointers. It refers to an actual memory location. So what is it pointing to right now? Nothing, right? In fact, you know what? Let's use our Python tutor over here. And I'm going to go, I'll keep that function, but I won't call that function. Instead, I'll go ahead and put in the code that we've been typing here and visualize this execution. Okay? So somewhere in the program stack, we've got that variable x, and it has 42. Right? Oh, looks like it, all right. It compiled it away, right? It optimized it. Because I never actually used the variable and never actually created it. Darn it. All right, so what is it actually pointing to? Well, let's go ahead and make it point to something, right? What's it pointing to right now? Who knows? Garbage. In fact, if it had not optimized that variable away, the way that this visualization tool refers to uninitialized pointers is with this poop emoji over here, right? It's garbage, right? What's it pointing to? It could be pointing to anything. It could be pointing to a memory location that doesn't belong to your program. It could be pointing to a memory location that doesn't even exist, right? Some random number. So let's make it point to something. That something that we'll start out with is null. All caps, N-U-L-L. Right? That is a very special a pointer that refers to nothing. It's not pointing to some random location. It's pointing to the null location. Right? That way you can check to see, is it null? Is this a pointer that points to something, or is it a pointer that points to nothing? Right? You can check for null. If ptr to x is equal to null, then printf invalid pointer. Right? Not pointing to anything or whatever, and handle it that way. This is called a null pointer check. Right? We're checking to see whether or not the pointer is pointing to a valid memory location or to nothing. Right? That's what null is. So now what I'm going to do is I'm going to make actually let's go ahead and embed our notes here as we go along. I'll go ahead and leave it like this, and I'll put in here creating an uninitialized pointer has undefined behavior. Right? It can point to a memory location that doesn't belong to your program. And we've seen the consequences of that if we try to use it. Seg faults. Right? It points to a memory location that doesn't belong to your program. You try to access that memory. The operating system says, no, that memory does not belong to you. There might be something sensitive stored in there, like passwords or crypto keys or something like that. We're going to kill your program with a segmentation fault. It can point to a memory location that doesn't exist, right? Etc. It's undefined, right? You can point a pointer to the null address using the following syntax, ptr to x. Right? You can also test for it. You can test for nullity as follows. Right? But now let's go ahead and make the pointer point to something. Make the pointer point to the variable x. To do that, I need to get the memory location of x. If I tried this, and we'll come back to this and see why this is wrong, right? The thing on the left-hand side is a memory location. It's a memory address. The thing on the right-hand side, that's a regular old variable. It's not a memory address. I can do something like this, but it's going to be invalid, and we'll find out why later on, because it's going to point to the memory location 42. Memory location 42 may not, but probably doesn't belong to me. It may not even exist. Same reasons as above, right? That this is wrong. So I need to make it point to the actual memory location of x. X, when I just use x, that's getting the contents. And remember, contents and address are different. So how do I get the address of that pointer? I put an ampersand in front of it. Does that look familiar? Think about for week 1, 2, where we used scanf, and I said magic for now. We put an ampersand in front of the variable because we were going to pass it by reference. We were getting the memory location of that variable rather than using the variable itself. Right? Now this is actually pointing to x. Right? The ampersand gets the memory location address of a regular variable. Right? And so now the thing on the left-hand side is a pointer. The thing on the right-hand side is a pointer. They agree now, right? That we can make a pointer point to a memory location. Now let's go ahead and take this. I'm only really interested in the code, not the comments that I've been embedding. But now let's go ahead and visualize this, okay? And hopefully it won't optimize it away anymore because, oops. Okay, null is undeclared. Let me edit the code. Where is null declared? In the stdlib. That's why. It worked. It should have worked, but apparently this is not bringing in the standard library, so I need to do it explicitly. Close that, forget it. Okay. So now let's walk through this program. First of all, I create a variable x, and thankfully it didn't optimize that other variable away. And it takes on the value of 42. I've got this ptr to x, and apparently now the actual visualization here is just a question mark. What's it pointing to? Who knows? But after line 20, it will point to null, right? This special memory location. And if it's null, then we'll go ahead and print out invalid pointer, right? And that ends up printing out invalid pointer. Now what I'm going to do is make it point to x. There. That's literally what it's doing, is pointing, referring to that memory location. This is why it's called memory references or references. And why we colloquially call it a pointer, because it is pointing to that thing over there. Right? And that's how they've chosen to visualize this thing. PTR to x is pointing to x now. Okay? So that's pointers in a nutshell. Here are some pitfalls. Right? Pitfalls. In fact, before I do that, let me go ahead and make sure that we have this code. Oh, nope, not over here. I'm going to go ahead and take this code and put it into the notes so that we have it. There we go. So now pitfalls. Uninitialized pointers have undefined behavior. Using invalid pointers can result in segmentation faults. When you forgot the ampersand in a scanf statement, that resulted in a segmentation fault because you were getting you were using the contents as the memory location. Okay, that's why they say you're trying to access a memory location that doesn't belong to you. Right? You should always make a pointer point to a valid memory location that belongs to your program. Right? So what do I mean by that? Let's come over here and let's start screwing up, right? So for example, let's go ahead and retain all of this. But instead of making it point to null, let me go ahead and make it point to x. Right? Now, I'm going to print out the values here. Printf x is equal to %d and the line. Right? And so we'll have an x value here. Printf pointer ptr to x is equal to, now what's my placeholder for a pointer? What do you think? ptr to x. I'll give you a hint here. It makes sense. Oh, that would actually make sense too. I was thinking more in terms of letters though. P starts, or a pointer starts with a P, so we can treat it as a pointer here, right? Now what I'm going to do is I'm going to dereference it, F. So you can, or in comments here, you can get and manipulate the contents of a pointer, or of what a pointer points to, using the dereference operator. And unfortunately, it is also a star, right? So printf, the contents of memory location %p, right, are %d. I'm going to dereference it. So memory location here, that's ptr2x, right? I'm going to dereference ptr2x to get to what's stored there. And I'm going to comment this out first because this is actually going to, hopefully it'll kill our program here. Let me go ahead and show you what it looks like when I do remain safe here, all right? There we go. First of all, there's a warning. You shouldn't be doing that. The thing on the left-hand side is a memory reference, a pointer. The thing on the right-hand side is not a pointer. These things do not match. But it's only a warning. It's letting me do whatever I want. So when I go ahead and run this, we see that x has a value of 42, as expected, because it's a regular old variable here. But what is pointer to x pointing to? What memory location is this? Does anybody speak hex? All right. Hex to decimal. Hex is base 16. So 0 through 9, and then A through F. And if I've got a hex number of 0, or 2A, convert that to, that looks familiar. It's pointing to memory location 42. Now, do you think that randomly the memory location 42 belongs to my program? Probably not. So when I go and try to dereference it and get what's ever stored at that memory location, I wonder what happens. Right? So still warning here. Segmentation fault, just like I said, right? I'm trying to access memory location number 42, address 42, or in hex speak, 2A, right? That's really low memory location, probably belongs to the BIOS or an operating system or something like that. And it's detecting that you can't do that and it kills my program, okay? So attempting to access memory locations that don't belong to you are going to be segmentation faults. And here's the demo that I just gave, all right? There we go. Observe that you can convert a pointer back into a regular old variable in order to assign or a value or access its value using the dereferencing operator, the single asterisk. So this is just something, it's like me when I was taking like calc 20 years ago or whatever it was, right? I never remembered what the derivative of sine was. Was it cosine or was it negative sine? Negative cosine. Cosine, thank you, right? I still don't remember what it was. So what I did is I took a post-it note and just put those two things on there. Sine goes to cosine. The derivative of cosine goes to negative sine, right? I was right, right? All right, so I do remember it after 20 years because I put it up on a post-it note and I had it above my thing the entire time that I was taking calc, right? Same thing here. How are you going to remember these operators? Remember. that a pointer, or a regular variable, can be changed to a pointer or reference using the ampersand, right? A pointer variable can be changed to a regular old variable using the star, right? It's just that's the order that you're going to have to remember. So put that up on a post-it note, put it next to your workspace or whatever, and just remember that that's the order, right? You can switch those orders and get completely weird behavior that's going to crash your program, result in a segmentation fault, right? For a lot of the issues, though, of course, yeah, keep working. A lot of the issues here, your compiler will try to save you from yourself. Right? Your compiler tried to save you from yourself when you forgot the ampersand, as long as you turned on all the warnings, W all. Right? I wonder if this is going to come up with any more warnings here with W all. Nope, just the same warning there. But thankfully now it's a standard warning. Okay. All right. So how does this help? Oops. So what? Why do we need why do we need reference variables like this? It allows us to change our to actually achieve what we were trying to achieve here. Okay. I do actually want to write a function that will take and receive two variables and swap them so that the original variables are now swapped. I can do that with pointers. Instead of giving you the actual values 10 and 20, and then you've got your own copies in your stack frame, what I'm going to give you is two pointers that point back to the original variables so that you can manipulate them and you can change them. Right? How are we going to do that? Well, we're going to have to change this so that it receives two pointers instead. Int A is not a pointer. What is a pointer? Int star A. Int star B. Now that's no longer receiving integers. It's not receiving 10 and 20. It's receiving the memory addresses of whatever variables held 10 and 20 in the original function. Right? I can't manipulate them like regular variables because they're not regular variables. Right? Temp is a regular variable. How do I convert A into a regular old, it's a pointer now, how do I convert it into a regular old variable so that I can get that 10 out of it and put it into temp? So go back to our post-it note. How do I take a pointer variable and change it into a regular old variable so that I can manipulate its contents? Star. Likewise, star, star, and star. I don't need a star in front of temp. Why? Temp is just a regular old variable. It's not a pointer variable. All right. Now let's come down here and redeclare. In fact, I'm going to declare it as x and y to really drive home the point here that these are not the same variables as this a and b up here. Right? X and y are regular old variables. Now I want to swap them. Right? Can I do it like this? Again, x and y are regular old variables. Is that what swap is assuming that they are? Nope. They're receiving pointers. So once again, my post-it note over here, how do I take a regular old variable and change it into a pointer? By placing a ampersand in front of it. And ampersand. Now what this ends up doing is it ends up passing these by reference. Okay? That means that the memory locations of x and y are passed into swap. Let's actually see that in real time here. Printf. In swap, we'll say that received memory location %p, which contains %d, and the line. And then I'll actually print out a, and then I want to change a into a regular old variable so that I can get the contents stored at that memory location. Right? And I'll do the same thing for b. B and b. Okay? And then I'll swap them and I'll return. Okay? And then down here, I'm going to print them out. Printf x and y are now %d and %d and the line x and y. Okay? Let's see this in action and exactly what's happening here. Okay? So I've got x and y, 10 and 20. I'm about to call the swap function here. Right? It receives a and b, which are now what? Not regular old variables like this is, int and int. It is a pointer and a pointer. Next, a. They point back to those original values, x and y. We have our own a and b in our own stack frame, but a and b are now pointers that are pointing to another memory location. And it's our program stack, so we have a guarantee that we own those variables. We own that memory space. So we're not going to have a seg fault here. I print them out, and we see that we receive memory location, blah, 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 right? It's just hex speak. And then another memory location, which is slightly different, which contains 10 and 20 respectively. Okay? So now it'll actually swap them. How will it swap them? By jumping to these locations, right? It jumps from A, I can highlight that, which is pointing to 10, takes the value and stores that into temp. It then jumps to memory location B, A, and then puts a B and takes whatever's stored there and copies it to whatever is stored over here, overriding the original 10, and then 20. And you see here that the original x and y have been swapped. So when we return from this function, we successfully did it. Yeah?
Why did, you mind go back?
Oh, sure. I can do that.
Why does A point to X and B to Y?
It doesn't. It's just that it's, here, let me highlight B. B is actually pointing to Y. It's just that they got crisscrossed.
Okay. Like, is that, could B ever point to X?
If I made it, yeah. If I wanted to, I could say, well, here, let's just switch them around if you want.
Oh, it's just order.
Yeah, it's the order. Yep. Undo. There we go. I can make a pointer point to anything, including illegal stuff, right? Memory locations that don't belong to me, memory locations that don't even exist. Yeah.
So inside the swap function, it's always an order A, B?
Yeah, well, I mean, it depends on, I swap them in X, Y, so A is going to point to X, B is going to point to Y.
Okay, I
Right.
see.
That's the order of the, that it receives them in according to the parameters.
Okay.
If you've got a parameter list A, B, C, and you pass in 10, 20, 30, 10, 20, 30 is the order.
Okay,
Right.
thank you.
Okay? So what? It allows you to pass variables by reference to a function. That function can then manipulate the original variables. Right? So it can change them. It can update them. It can do whatever it wants to the contents of that memory. Okay? And this is actually a pretty powerful thing. Most programming languages do not allow you this kind of access. This low-level memory direct memory access is not a thing in the vast majority of programming languages. C, C++, they allow that because they're both really old school. Java, there aren't any pointers. There are some languages that have quasi-pointers where you can pass stuff by reference. PHP, for example. Python, I don't know if you can do that in Python at all. But in any case, yeah, I really doubt that you could. I'd have to look that up. But certainly none of them allow you to create a pointer variable as what we call a first-class citizen. So an integer on a double, a char, those are all first-class citizens because they are built into the language. There are second-class citizens later on when we start making our own types, enumerated types, structures and stuff like that are not built into the language. Instead, they're user-defined types. So if something is built into the language, it's usually referred to as a first-class citizen. Pointers in C are first-class citizens because they're built into the language. No other programming language that I know of, except for C++, does that. Right? This is something almost unique to C. Okay? So, and it can get you into lots of trouble, right? Another pitfall. Make sure your pointer points to the correct type of variable. What do I mean by that? Let's come over here. And let's say I've got an integer, let's say I've got a double now. Double is equal to 42.45. Right? And what's going to happen here when I attempt to make pointer to x point to x? Well, first of all, what type of variable is x? It's a double. What type of variable is pointer to x? An integer pointer, right? So we'll make it point there, and then we can actually manipulate the contents of it. PTR to x is equal to, I don't know, 101. Right, there we go. But actually, before I do that, let's go ahead and see what happens here. So x is equal to not a double, it is now a floating point number, a double, or it's no longer an integer is what I mean. This is still just a raw memory location. So it's going to be some hexadecimal number, who cares, right? It's something that's meaningful to the computer, but not to us. The contents of that memory location are blank and blank, right? So when I go to dereference it, I will treat it as a floating point number or a double or a decimal. I don't know. Let's find out. First of all, I hope that this will, yeah, it's going to be a warning, right? Wait, you're mixing types here, right? You've got an integer and a double, and you're mixing this all up all over the place. So what would you expect it to output here? 42.45? Maybe. Let's find out. Okay, it does, right? Maybe I want to switch this around. Make this into an integer and make this into a double. There we go. There's an integer now, right? Pointer to x is that. It's a pointer, and it's still a double, or it's still an integer, so this will work. Right? Again, we're mixing types. Okay, 42, and that makes sense because we've got that, right? But now let's go ahead and create, or change its value here to 101 and print everything out again. Let's find out what happens now. And still just warnings, no errors. You're perfectly fine to do this if you really want to do this. It's warning you all over the place, and you shouldn't be doing that, but there you go. Core dump with segmentation fault. What happened here? Okay. So does anybody remember how many bytes an integer takes? 32 bits, that's a hint. So how many bits in a byte? Oh, no? We don't know that? All right, so there are 8 bits in 1 byte, right? Everything is base 2. And then there are 4 bytes in 1 integer, so 32 bits, right? 32-bit system, 64-bit system, all that kind of stuff, right? So an integer is 4 bytes. What about a double? As the name implies, how many bytes is it? Double the size. There are 8 bytes there. So when I try to make a pointer that it expects 8 bytes, point to a memory location that's only 4 bytes, guess what happens? It's going to think, oh, these other 4 bytes belong to me, right? 42 is stored right here. But I'm going to go ahead and expand that out and treat this stuff as part of the number. Well, what's over here? Garbage, right? It might not even be garbage. It might be valid memory stuff that has nothing to do with 42 over here. So in the best case scenario, I don't get 42. I get 42 and however this garbage over here is interpreted, right? And in this case, though, it resulted in a segmentation fault because when I tried to go and set 101, instead of setting it just in these 4 bytes, I tried to set it in these 8 bytes. So did these 4 bytes belong to me? Apparently not. And that's why it said segmentation fault. All right? You're trying to set all 8 of these bytes, and you can't do that. All right? So make sure that it's pointing to the correct type of variable. In other words, an integer, int star pointer, can point to a memory location that stores an integer, but it should not. Again, it can, as we just seen, but it should not point to any other type. say a double, char, etc. A double star pointer can point to a memory location that contains a double, but should not point to any other type, etc., etc. Right? You can have a char star. Oh, hey, that looks familiar. Char star. Where have we seen that before? Here, strings, right? We'll get into arrays next here. But wait a second, I see something else now. Now that I know what star means, it means a pointer. I see char star star. What do you think that is? A pointer to another pointer that points to a memory location that contains a character. In other words, we've got a two-dimensional matrix of characters. If you look at each row is going to end up being a string. The second row is another string. The third row is another string. Right? This is how we have an array, a collection of strings. Right? Again, we'll get into that later on with strings, probably after the midterm. Okay? Otherwise, that's enough for pointers for now. Except that we also have Java, right? Java, this is really easy, has no pointers. Right? You generally do not manipulate memory contents directly in Java. Right? You let it take care of that stuff for you. Java is what we call memory managed. It's a memory managed language in that you don't do memory management yourself. That low-level stuff of making sure that this piece of memory is valid, that it's 4 bytes and only 4 bytes, and that this is 8 bytes and this is only 8 bytes, and you're only accessing what you should, and not directly accessing the memory. Java takes care of all that for you. Right? In fact, it puts a barrier between you and the low-level kind of memory stuff so that you can't manipulate low-level contents of memory like that. It doesn't want you to do that, and it comes at a price, right? The Java virtual machine is managing all the memory, doing all the garbage collection, making sure that everything works correctly. You pay a price for that. You pay a price as far as performance goes, right? But you know, there's trade-offs everywhere. With great power comes great responsibility in C. If you can directly manipulate the contents of memory, right, then you can do some really powerful stuff. But if you don't do it carefully and you don't do it correctly, you can do a lot of damage, right? You can access memory that doesn't belong to you, and if the operating system has a bug that allows you to do that, right, then you have Heartbleed. Do you remember Heartbleed from several years ago? Heartbleed bug, right? There we go. So if you want to, you can go ahead and read all about it. It was basically a flaw in OpenSSL that allowed a remote computer. All you had to do was start pinging this web server that had this bug in it, in its system, and you would randomly get back chunks of memory that didn't belong to you as a user, but belonged to the program because you know it owns its own memory. Well, guess what it stored in its own memory? It stored images that it was serving on the web server. It stored HTML crap that was being stored on the web server and served to users, but it was also storing SSL keys, right, cryptographic keys, passwords, et cetera, et cetera. So if you were getting these random chunks of memory, right, by invoking this bug here, yeah, for the most part, you'd just get back garbage, right? But every once in a while, you would get a key, right? And all you had to do was keep doing this over and over again and finally get something of value, and then now you could decrypt all the traffic going between those two servers. Not just your traffic, but everybody's traffic. Right? And it was a heartbleed bug. Again, it's because it was written in C, low level, allowed direct memory content access. It wasn't that simple, but that's the basic idea. Right? That with great power comes great responsibility, and making sure that it's actually correct. Right? But with Java, yeah, you can't even do it. Right? They took that away from you. Right? But again, it comes at a price. But by default, all primitive types are passed by value, right? In other words, i.e., you cannot write a swap function or swap method that works in Java. It is impossible. You can't do it, period. There's no way. Well, that was kind of a toy example anyway. Why would you ever want to do that? It's just 3 lines of code. Why are you going to put that in a function? Just do it, right? But also, all object types, right? They're like, for example, string, integer, right? Integer, and double are passed by reference. Right? So if it's got a capital in it, that means it's a class. When you pass that to a function, it is like passing, like we just did here and with a pointer, right? Except that it's opaque to us, right? It's being done automatically under the hood. Right? Does that mean that we can write a swap function? The answer is still no. You still cannot swap them. Why? Because all built-in types, or all, let me preface that with most, built-in types, such as string, integer, double, big D double, big I integer, are immutable. So what does immutable mean in English? What does mutable mean in English? Mutable, mutate, change, changeable, right? Immutable means unchangeable. You cannot change the value of a big I integer or a big D double after it's been created. Don't believe me, right? I could do that all the time, right? Double 42. I can change x is equal to 101, right? And I can print them out. Why are you complaining? 0.5. There we go, 0.5. System.out.println x. Let's print it before we change it. Let's print it after we change it. Professor, you're lying to me. I can change it. I didn't change it. I changed what it referred to. Right? So now think of it like this. In memory, there are actually 2 numbers, 42.5 and 101.5. As of line 9, x is referring to the first one. Then it gets printed out 42. In line 13, I don't change the contents of 42 of that value, right? And unfortunately, I don't know if it's going to show up on the stream here, but I've got 42.5, and somewhere else I've got 101.5, or yeah, whatever, right? And there's an address here, ADDRA and B, ADDRB. On line 9, x is referring to this memory location right here, the one storing 42.5. After, and then I print it, and then on line 13, it changes. X is now referring to this memory location over here. Did I actually change the original contents? Nope. The original contents are still here unchanged. They're now garbage because I have no reference to it, and so the Java virtual machine will say, okay, I'm going to reclaim that memory and maybe reuse it for something else now. Right? But to create a new variable, memory location, places 101.5 in it and makes x refer back to that location. That's how this is working. So I still can't do it. I still can't do a swap because it's immutable. Once it's been created, you cannot change that. Right? You can change what it refers to and create a new variable, but both of these, you can't change the contents there, you can't change the contents there. That's not the same thing as a little d double. If I have a little d double, that is referring to one memory location, and I can change that all I want. I can manipulate that, I can update that, I can change that as much as I want because it's known as a primitive type. It's a built-in type. But when I've got a big D double X, it refers to a memory location. Changing its value changes its memory location. It does not actually change the contents up here. One very direct way of seeing this is say strings. And again, we wait for strings for later on. Hello. There we go. Oops, I misspelled it. I wanted to, it's LO, right? I want to change that. S, no, wait, let me change it like this. I want a exclamation point in there instead. So I want to add an exclamation point. So how would I do that in Java? S is equal to S. How do I concatenate? For those that already have some Java experience. How do I add exclamation point at the end? How do I add it? Right? Append it, concatenate it, just the plus operation here. Right? System.out.println S. Again, we see this working. Right? Hello, and then hello has been changed. It looks like the variable S has, whatever was stored there has been changed. It hasn't. I'll prove it to you. Let me go ahead and grab the original reference up here before I go and change S to something else. And then I'll print out S, and I'll print out A. If I were actually changing the contents of memory location S, then we would see hello exclamation point in both of these instances, but we will not. We will see, oh, here, I had to save it, sorry. We will see that the original hello without an exclamation point is still there. Right? If you want, so further proof here, again, going back to the original would be double X is equal to, not yet. Actually, no, let me go ahead and go with integer. Integer X is equal to 10, right? Well, it's not that. Now, I like the string one example better, right? Because it's not all apparent when it's just numbers. But it should be absolutely clear when it is a string. I'm not changing the contents of the original string, right? Somewhere in memory here, I've got hello with no exclamation point. Then S is pointing to that. I make sure that A, is it A? Yeah. A is also pointing to that. Then on line 13, when I create a brand new string here, hello with an exclamation point, I am changing S so that it refers to this new one over here. And you can see that A is still pointing to the original string hello over here. It can't change the contents of this memory location because in Java, these things are immutable. Once they're created, you cannot change them. All right? That's all the built-in types in Java. And before you go thinking, well, that seems even more restrictive, immutability is a very, very good thing. Right? It is something to strive for and hope for and design in all of your stuff because it gives you thread safety for free. Right? If nobody can manipulate the contents of this memory, then you have a guarantee that nobody will manipulate the contents of this memory. So if you've got multiple threads, a program can have multiple threads so that you can run on multiple processors. There's not a processor today, even in something as simple as a phone, that doesn't have multiple cores on it, right? And with multiple cores, you can run multiple threads. One program can run multiple threads in parallel, right? So two threads in parallel at the same time. And unfortunately, you get into a thread safety issue here. If this thread manipulates the contents in this memory location and this thread manipulates the same contents, you can get into race conditions, right? Which one gets there first? Are they going to be fighting each other? But if you've got immutability, you've got a guarantee. Thread A is pointing to this memory location. Thread B has a guarantee that thread A cannot manipulate the contents here, right? It's safe. And you get thread safety for free, right, by having immutability built in. It's a very, very good thing. Right? We'll revisit that later on. Okay. Any questions? All right. We'll do more on pointers later on, and more on. This opens us up to error handling, which is actually going to be our ultimate focus here.